Let's take a look at the optics at play during the observation. What were the conditions at the time of the observation? The temperature most of the day was at 25 degrees. Humidity was at 45 to 46%. Visibility was extremely good. The wind was very low at 3 to 5 miles per hour. The sun, being the main driver of the atmosphere, was low in the sky. Ideal conditions for the layering of the atmosphere. We see distortion of the turbine blades as they are rotating. The blades at the top have little distortion till they hit an atmospheric layer. There is over a mile in distance between the first and last turbine. The turbines all look out of proportion. The generator sections in the middle of the blades should reduce in size due to perspective. The yellow base's width should also be reduced. In this observation, they all look the same size. The same again in this shot. The furthest and closest base look the same width. They should look like this. The closest has been magnified by about a third. The furthest by over 2 times. It's the same again in this shot. This was the same throughout the observation. The further the turbine, the more magnification. This is what they look like on a sunny day. The oil tanker seen at over 20 miles. Seen at 2 points during the observation. Initially thought to be different ships. After checking direction, the timings, and frame-by-frame analysis, both are the Eagle Kinabalu. The transformation was caught in the observation. The first sighting, the wind speed at that point, reduced the height of the dense layer to the lower main deck. As the ship moved into a layer of air, at roughly the same height as at our turbines, the transformation can be seen. The atmosphere layer height at our turbines would be at this level on the ship. At the first observation of the oil tanker, there is a low layer of denser air. The less dense air above is magnifying the whole ship and at the same time stretching the image we see. The smaller ship is what we would see with no dense atmosphere. Next, the magnification due to the density of the atmosphere, then the distortion at the top. As the ship moved to the higher level of density, below the yellow line, it is compressed and stretched out. The same as out turbine bases. The funnel in the upper layer is now magnified to look bigger at the top. As we look across the sky, it may seem like an endless expanse of blue or gray. In reality, it's teeming with tiny particles of water vapor. They have a significant impact on the magnification of objects, sometimes creating an almost surreal level of magnification. When light passes through water particles in the atmosphere, it is refracted and scattered in various directions. This creates a magnifying effect, making objects appear larger or closer than they actually are. For example, on a misty morning, a distant mountain range may appear more defined and closer than on a clear day. With minimal particles of vapor in the air, the sun looks small. When the vapor builds up, each particle acts as a lens. The sun is then seen larger than it actually is. The higher the moisture content and size of droplet in the air, the higher the magnification. The moisture content or amount of water droplets per cubic centimeter of air magnifies objects within or beyond it. Looking through a layer of air with the same moisture content, an object close to the observer will be magnified less than an object further away. As the object's light passes through each layers of moist air, each layer magnifies it more. The further the object, the more layers of magnification it passes through. We see the moon in the sky as the sun is just about to rise. Note the size of the moon through the vapor-rich atmosphere. As the sun rises, it drastically reduces the amount of vapor in the air. As this is happening, the moon can be seen to shrink in size. As the water vapor in the air is reduced, so is the magnifying effect. The same again with the sun. As the camera rises through less vapor-rich air, it gets smaller. When the air